by such a profound conclusion that life seems to be one-handed. And it is remarkable that this particular statement by Fisher in 1894 is borne out even today. Almost without exception, all the amino acids, the proteins, they are all left-handed, and all the sugars are right-handed. So, whether this fact, which is true today, was it true even at the beginning? The point is homochirality a precondition for life? So this is something, a question which is very profound. If that is the case, then we have to think in terms of processes to bring out the homochirality even before talking about the life. The reason is the point, the life, all these things are all polymers, the DNA kind of thing. And Joyce and others have done some experiment in homochiral monomers, and they found out that if you have got a left-handed solution, if you want to polymerize this, you need only left-handed thing to add, left-handed monomers to be added. If you have got the wrong-handed, if you have a right-handed monomer, then the polymerization stops. It's a really termination of this thing. This was shown by Joyce et al. In 1984, and this has been shown for the ribonucleides by Joyce and poly-L peptides by Blair and others. So it looks as though, since anyway we need it's not a monomer like biomolecules by no means, or monomer, they are all polymers, and the polymerization process definitely requires the presence of homochiral molecules. So it is very clear that if you are talking about origin of life, you are talking about the origin of homochirality. That's almost a precondition. So once this is the case, it is very clear that the ancestral biomolecules, the primordial biomolecules, fixes the handedness of the subsequent polymerization or whatever process it is. And one thing which is very interesting is, for example, we have the biochemistry, with all the biochemists would know, there are diastereomeric interactions of L amino acids and D sugars. This connection prevents the formation of L amino acids, N and L sugars. You just cannot have the combination of L amino acids and L sugars, or D amino acids and D sugars. But it is equally likely to have D amino acids and L sugars, which is like a perhaps anti-life kind of a thing. The mirror image of the life molecules, we have L amino acids and D sugars, so we can have it. So you can ask me, but whether it is a chance that is responsible for the terrestrial life having L amino acids and D sugars, or is there any fundamental principle involved, a universal principle, as we're talking about, Hugo was talking about, whether there is a universal principle involved in this. And it was Louis Pasteur again around 1894, who said that it should be a universal principle by which the handedness was chosen. It is not by chance. So, though it is equally likely to have a L amino acid D sugar as well as the D sugars, D amino acids and L sugar, we have in this terrestrial life, almost all the life forms, we have this particular lipoproteins and dextrose sugars. And at the time when Pasteur was making this suggestion that there should be a universal principle, universal force, which is responsible for selecting this handedness. There was the weak interactions or the strong interactions were not discovered. And at that time, the only interactions, the forces which they were aware of are the electromagnetic force and the gravitational force. And both of them do not distinguish between the handedness, whether it is left-handed or right-handed, both of them act equally. There was no problem. So there is no selection in that. So it was really remarkable that Pasteur believed, even at that time in 1894, when the whole forces are equally, there was no stereo selection in that, and everything was chiral, all the forces which were known at that time. But still, he said there should be a fundamental principle, by which this stereo selection was done at the ancestral biomolecules. Subsequently, in the 1920s and 30s, we have the discovery of strong and weak forces, and it is remarkable that in 1950s it was discovered that the weak force is higher. The weak interaction that distinguishes between the left-handedness and right-handedness. So, it is natural. Maybe this is responsible for bringing out the chirality, the homochirality which you are talking about, the chirality of the ancient biomolecules. Whether weak interactions played a small role. Is there any role of the weak interactions at all? That is what we are going to examine today. On the face of it, one more thing which I want to tell you for the sake of completeness, until the 1960s, weak interaction and the electromagnetic interactions were thought to be two different kind of forces, electromagnetic force and weak interaction force. The weak interaction was mediated by the boson, intermediate boson charged with W plus minus, and the electromagnetic interaction was by photon, and photon having zero mass, the range, the electromagnetic force has a long range, and since the charge there, intermediate bosons, W plus minus, are supposed to be heavy, that is the reason why it is almost like point interaction, very close range, small short range for the weak forces. So this is very interesting because we are talking about short range forces bringing about the universality of the homochirality. So there should be some basic reason why this weak interaction should play a role in bringing the homochirality. And that is something which was possible once the unification of the electromagnetic interactions and weak interaction was done by Abdus Salam and Weinberg and Glashow in the 1960s. They said, in addition to the charge current interaction like the beta decay, which all of us know, which is a charge current interaction, we should have a neutral current interaction, just like the scattering of the electron of photon of the electron. We should have the same neutral current component of the weak interactions, which will be mediated by Just like the charge boson, the intermediate vector bosons, here it is the intermediate vector boson, neutral intermediate vector boson, which is given the name Z. So Z0 is the force which is there. Again, this is also heavy, which should be because it's a short range one. So once this particular thing opened up, then it is very clear that electrons can interact with the neutrons, which was plenty in the nucleus. So this particular thing is going to create, there should be some, due to the interaction of the electrons with the neutrons, mediated by the Z0, we should have a change in the energy due to the parity violation. And this particular parity violating energy shift for the L and the D isomers or the L and D enantiomers should be calculable. And if our hunch is right, that weak interaction should play a role, there should be energy shift between the L form and the D form. And this parity violating energy shift is calculable because we know the Hamiltonian density, we know the matrix elements, we know all the things which are needed for this. So this was the challenge, and then it was found that it is really indeed so. The parity violating energy difference between the L and the D forms is calculable. The Hamiltonian energy density is PV, and we have the current electron and the nucleon, mu and mz0 square comes there. Gn is the coupling constant. So coupling constant, as we saw, it is 10 to the minus 11, and then mz is really very heavy, so around 80 GeV is the container. So we can see that it is a short range one. And so this being the case, immediately you will ask me, so this is kind of atomic, kind of the elementary particles kind of interactions, how this is going to change the energy of the molecular arrangements, how it's going to be come out. And this comes about because, normally what happens is you have to just essentially, what is the calculation you have to do? You have to just find out what is the ground state wave functions, ground state energy difference, whether there is any energy differences due to this ground state. And if there is no spin orbit coupling, then of course there is not going to be any energy differences between the two. Precisely because there is a spin orbit coupling in the, for example, the thing, then we can calculate the parity violating energy differences between the J and K states, and this is the what happens is we have to sum over all occupied molecular orbitals, that is the J, and we have to sum over all unoccupied molecular orbitals, that is the K, and this is unoccupied and occupied, and this is the energy differences between the two, and psi j, j, k are the wave functions and the E are the energies of these. And then we can calculate this kind, usual kind. This is something which is routinely done by the molecular orbital calculations. And what is interesting is the following thing. We can see the analogy between the parity violating energy difference, strength PJK, and the optical activity, which is given by the rotating of the optical, this rotating of the element is the imaginary part of the psi of mu, psi A, psi M, psi naught. In optical activity, V, PV and mu are the parity odd things. because they are all vectors, polar vectors, and the spin orbit and the M or the even axial vector because they are all even. So essentially this you can see from here, what you are seeing is the parity violating interaction is having the opposite sign of the optical activity. Essentially that's all that it is. You can see this for the line. And this being the axial vector. So the calculation is, I don't want to go into all the details about this. This is essentially your kind of molecular orbital coefficients and molecular orbital energies, matrix elements of P series O from the atomic orbitals. And one common substance is the following thing. The parity violating energy difference is all over 10 to the minus 20, 10 to the minus 10 or 3. Essentially, this, you can just take this particular thing, 10 to the minus 17, 10 to the minus 14 kT for typical biomolecules. You may say it is extremely small, but still, even how small it is, we know that this is going to lead to some differences at room temperatures between there is a free selection now. We can see here that we have the L and D forms, that is equivalent to around 10 to the minus 17 to 10 to the minus 14. I have to remind you that even though this may look extremely small, it has been verified that the proteins which are going into our life forms, the L-alanine, L-valine, L-serine, L-aspartate, etc., they are more stable than their DNA. Purely from the stability calculations, it is very clear that we have landed the interesting observation of the ancestral biomolecules or of L variety or more stable. This particular thing has been verified extensively in various calculations. And recently, some of the experimental arrangements are being done, and they seem to arrive at they have in Camphor, they have done this experiment, and they have seen the stability of the L variety. But this is as far as the amino acids are concerned, the proteins are concerned. Of course, you can ask me, after all, this thing doesn't distinguish only between any L form and D form should have the same kind of problem. So in the sugars, what is the case? And the sugar, all those product of sugars, H2CON, for any equal to 3 to 5, calculations have been done. And there is some kind of a problem which we face. For example, glyceraldehyde, which is n equal to 3 mm here, it has been very clear in the PVED stabilizations. Straight away it tells us that it is D form is mostly not the other. This calculation has been done and it has been nice. The same way deoxyribose, that D variety is PVD stabilized. Essentially the C2 endo form of the found in the DNA, that is deoxyribose. C2 form found in DNA is again PVD stabilized. Again D form is okay. But there's a catch. D-ribose, this RNA which is found in the C3 endo form RNA, found in RNA, is less stable compared to the L form. This shows that at least in the 5 minutes.
No.
Oh no. Okay. So anyway, let me just so the L form is less stable. The L form is more stable. L sugar is more stable than this one. So naturally this is a problem. So it was a bold suggestion that probably B ribose is not the belongs to the ancestral molecule. Maybe the parent of the ribose, they may PV destabilize in the D sugar, and essentially what we say is B ribose is not prebiotic. I mean, to make a conclusion based on this kind of theoretical calculations of weak interactions may sound very very odd, but the weak interaction people will stuck to that. And then what we find is, if D Ramadurai is a parent of the parent, then we found this particular thing again is stable. D form is stable. So D ribose is not this one where it is a parent is the same which is selected, PVD selected. So if this is the case, then it is something which is very nicely done. And actually there is another form, beta D ribose. I don't have time to go into all these chemical things. Let me just come to the process transparency perhaps. Essentially what we find is the weak interaction can give preferentially L amino acids, and in the case of D ribose also the current D ribose, D sugars, but extremely small, the order 10 to the minus 10 to the minus 14. And even though it is very small, I had to, for example, the subsequent two talks, you are going to hear about the amplification by polymerization and other processes. And actually Axel is going to talk about this, Thomas is going to talk about these things. There, what they are saying is, their conclusion is, if there is a fluctuation, if you have one homochiral, one initial thing of the extremely small, it may be just a fluctuation, whatever it is, if you have L selection of the L molecules or there, L molecules there, that is going to grow in the polymer chain, and you can have a complete homochirality within the reasonable time. But we have to remember that they can equally likely with D amino acids and L sugars. If that's the case, the same kind of growth can be possible with that kind of models. This is what my impression is. So essentially you need to have a principle by which this can be selected. And that particular universal principle is there. With a weak interaction, he is going to provide you preferentially L amino acids and D sugars. And this can be amplified further by this kind of processes. But being ambitious persons, the weak interaction people, we felt there should be some better way of even weak interaction, instead of just stopping at 10 to the minus 17, 10 to the 14, is it possible to have the kind of amplification of this to higher things by same weak process? And in this particular case, people have done the beta decay electrons are potentially polarized. These polarized electrons have these interactions, and then we find the inelastic cross section between the L and the D for the electron nucleon interactions. Again, have the same PVED kind of thing. So that particular thing is going to bring about the same kind of selection, and this is going to act because of the fact that we have lot of beta electrons taking place in the Earth, and then we say that this kind of thing is taking place. Natural radioactivity, whether it will bring about the thing. But the natural radioactivity, the beta electrons are so small in number compared to the kind of numbers which you are talking about, or 10 to the 15 kind of thing. So we were thinking of a better way. Yesterday, Anya was showing you, and Anderson was showing you, that our solar system came from a molecular cloud condensation which was exposed to supernovae. The same kind of supernovae explosions have been observed in night. We have very beautiful observations of neutrinos from a supernova from Magellanic clouds in 1987, and we have unmistakable proof that there are about 10 to the power 56 neutrinos of a few MeV emitted from this particular supernova. That is something which is a verified fact, observational fact. So these neutrinos, when they fall on the molecular clouds, then the same lepton-neutron interaction is going to take place. So the amino acids are going to preferentially, instead of the beta decay electrons, we have the neutrinos from the supernovae playing the same role, and then we can show that it can lead to a significant part of our biomass being subjected to this neutrino interaction and bringing out homogeneity. So it is possible that weak interaction is responsible, that supernova explosion is responsible for our existence. Thank you.
So, questions and discussion?
If we follow your assumption that D-ribose is not a primordial molecule, prebiotic molecule.
Please speak a little louder.
How does that fit with the conception of the RNA world?
No, but it's not necessary to be ribose. The D-ribose should be the prebiotic thing. We can have a glyceraldehyde as the prebiotic molecule there. What is wrong in having that?
No, I mean.
You're talking about amino acids. She is talking about the sugars.
No, that's not my part. Sugars also. D-glyceraldehyde is the one which gives the sugar, D-sugar.
The sugars were the L sugars.
Yeah.
The amino acids were also the amino acids.
Yeah, that's
and somehow I understand that if you have amino acids in L, then you can only have D sugars.
Yes.
That's what you said at the beginning.
This is what the stereospheric selection, this is what the di-stereomeric interaction between the thing is L sugar and D.
In that picture, would that mean that the L amino acids were first and then they forced the sugars to be D?
Yes, I agree. That's the kind of picture which we are arriving at. That's
So that's the case that would be...
No, because see, for example, ribose is extremely difficult to synthesize in any case.
Yeah.
That's the reason why it is interesting that this seems to be born out. I mean, this kind of ribose is the one which gives this problem for us. That ribose can be sort of synthesized this way kind of interaction by the amino acids and then bring the sugars. D-ribose is something like that. These few destabilized amino acids give rise to the D-sugars. D-ribose.
So where did you say this measurements took place?
What is it?
Where did you say the measurements took place?
I mean, for example, after all, when the solar system was formed, it was in molecular clouds.
No, the measurements.
The measurement by Mason and Tranter, I mean, Oxford, I think it was done in Oxford. 85 yeah.
But
Joyce et al, I think, is
in your list of the fundamental forces, you leave out one thing. That's
the Fields force. Yes,
no. That's the distance.
That's speculative. So I mean
the distance over which they do their interactions, and only
okay.
Yeah, only the electromagnetic.
Magnetic is long range because there is a
the gravity is long range. The other ones are restricted to the nucleus.
Yeah, because the short range, because of the intermediate bosons are carrier. The blue ones are very carrier.
Yes, but how do you then evolve the weak interaction from nuclear distances to molecular distances?
No, this is within the nucleus, within the atom. This particular thing is within the atom itself, this particular thing takes place. That interaction between the electron, orbital electrons, or the nuclear, the neutrinos impinging on the nucleons in the atom.
Yeah.
That is what the...
Yeah, but how do you get from the atom to the molecule?
No, molecules are already there. I mean, we are talking about the molecule in which.
Yeah, but how do you get the
spin orbit coupling?
No, because the
acts on molecules?
yes.
It's
No, not on the molecule. It's on the individual atom in the molecule. It decides. The force acts on the individual atoms in the molecule. It's not that first the atom thing and then molecules are formed.
No, but how do you get the weak interaction to spring?
No, for example, if you have
spring from the being an intra-atomic force to be
no, still we are talking about, no, so still we are talking about, see, after all, the thing is it is being exposed as a in the molecular form itself, it is being exposed to the neutrinos or the beta performance electrons, the atom in the molecules. The molecular strands are not broken.
But
you don't have to break the molecular strands to do this.
But I think the question is about the coupling between the nucleus and the electron, so the spin-orbit coupling,
yes.
which you said, of course, needs to be included in the calculation. So there is a coupling between the electrons that's going around and the nucleus, and that's a sort of fact from
that's
nuclear
okay.
physics.
Yeah.
Okay, but how do you get from having and now you're talking a solar system model for the nucleus, and that's not even quite okay. I mean, but how do you get from the spin-orbit coupling that
No, this particular thing, this coupling.
Wait now a second. How do you get from the spin-orbit coupling inside an atom to affecting other atoms? I mean, where does the
No, the point is, if you are having the energy differences, to be calculating this interaction.
Yeah, where do this come from?
This particular thing comes from the spin-orbit coupling calculation.
I mean,
For the nuclear.
clarification, isn't the Hamiltonian actually the Hamiltonian of the full amino acid? Or is it?
If the electrons are nucleon, that's atom, that's the kind of thing which you are talking.
It's not the full amino acid. I mean, when really would need a calculation, of course, a consistent calculation for the full amino acid, right?
Yeah.
So
Anyway, I think
your question remains open, of course.
Yeah.
Yes. And you mentioned a range of 10 to the minus 13 to the minus 17. Where did, or whatever, minus 20.
Yeah.
Where did this range come from? I was implicitly thinking the range comes from the fact that you have different amino acids. But now since I realized that the calculation doesn't actually cover the full amino acid.
And this is something which comes from the temperature at room temperature is not under minus 17.
So one last question here now.
What do you think about such an idea that if there is an interaction between weak force and electromagnetism, and especially the geomagnetism, then the directional rotation of the Earth could play some role, depending on which hemisphere did the first self-reproducing biomolecules arise.
I don't see the connection.
Well,
I'm not able to see.
so then there is a preferred hemisphere. If it was a southern or northern hemisphere, then the first self-reproducing.
I think he's saying that the magnetic field will have different, or can have different helicities in the two hemispheres, which is certainly correct. And that has to do with the fact that there is a rotation.
Oh. I didn't think about it, so I cannot say anything about it.
There is a related issue, of course, the fact that we have matter as opposed to antimatter also has apparently to do, and maybe Thomas can correct us here in the details, has to do with certain issues which can be related to magnetic helicity.
Sure.
So there's perhaps really some...
No, that is only if you are talking in terms of antimatter kind of a thing, otherwise anti-light.
Yeah, right. But there is
But the point is, we have the selection, preferential selection, which you require. For example, in your model kind of thing which you are going to present, it can be equally good with D amino acids and their sugars. I mean, as he would say that it may come by just chance that we are having there. Instead of chance, there is a method by which this can be done. This is what I am. The weak interaction preferentially selects the L amino acids D sugars. That's what. That's why I am interesting that purely from the point of view this that.
Right, thank you. So the next talk will continue on the same subject, the Axel Brandenburg.